Hello, calculus fans. Let's use spherical coordinates to parameterize a sphere of radius a. This seems to be the most natural way to parameterize a sphere. Remember that spherical coordinates look like this: x equals a sine phi cosine theta, y equals a sine phi sine theta, z equals a cosine phi, where phi goes from 0 to pi and theta goes from 0 to 2 pi. This is how you would parameterize a sphere, because these are spherical coordinates. I'm thinking of a as being a fixed number. Really, in spherical coordinates, we put a rho there and we let rho vary, but here it's going to be a fixed number. Of course, I could write this in vector form like this. That doesn't really change anything. All right, well, if we're going to use this to compute areas, let's compute r phi cross r theta. We're going to need that when we compute the surface area of the sphere. Now this expression is going to come up again. So what we want to do is perform this calculation once and never do it again. So if we compute r sub phi and r sub theta, we get these derivatives. And now we need to cross these. Now this is a calculation you should verify or do it through MATLAB. You should compute the cross product to make sure that we get the right thing. If you compute r phi cross r theta and do some simplification, then you end up with this expression here, this vector. All right, we're going to compute the length of r phi cross r theta. So we have to square the components that we previously computed. You should note that there's some simplification that can happen. What you should see is that a couple of these terms will collapse down. So for instance, these two terms, what can you factor out? A to the fourth sine to the fourth phi, and you're left with cosine squared theta plus sine squared theta. And there's more simplification that can happen. And each time you factor out something, you get to use the Pythagorean identity, and you end up with something that's actually quite nice: square root of a to the fourth sine squared phi. And of course, that simplifies down to a squared sine phi. And it's important to note that this is valid because phi runs between 0 and pi, so sine of phi is always greater than or equal to 0. That means we don't have to put an absolute value in here. Now we're going to be using spheres a lot, which means we're going to use this parameterization a lot. And we're going to need the value of the length of r sub phi cross r sub theta, which is we've computed as a squared sine phi. We're going to need that again. I'm never going to do it again. This is the last time. And I don't think you should have to go through all those gory details again. Now I want you to go through the cross product once and the calculation of the length once so that you have done it and that you've seen how it all works out, but I don't want you to have to do it again. Now don't skip over this. Don't just take my word for it. You actually need to go through and do all these calculations once. All right, now we're in a position where we can compute the area of the sphere. So the area of the sphere is the integral over the region D, which is the parameter space, of the length of r phi cross r theta. So we end up with the integral where phi goes from 0 to pi, theta goes from 0 to 2 pi, a squared sine phi d theta d phi. And as it turns out, this is actually a fairly straightforward integral to compute. We can pull out the a squared and then factor by phi and theta. And our final result is going to end up being 4 pi a squared. And you might even recognize this as the formula for the surface area of a sphere. Okay, that's all for now.